Chapter 20, Part 4, we're going to continue on with reactions of acid halides. Now, this next one is just a review, right? Reduction. You don't need to know the mechanism of this one, but you do need to know the reagents. And you do need to put the 1 and the 2. So LiAlH4 or LAH is lithium aluminum hydride. You're going to follow that up with water. This is going to take any of your carboxylic acid or carboxylic acid derivatives down to an alcohol or amine. We'll see that in probably in another video here. You're going to wind up with a primary alcohol in the case of the acid halides. Now, it does say excess, and that's true because you are also replacing that Z group, but I would just assume that you have enough here. It's not like you can control it and only partially reduce it. If you don't have enough LAH, you're just going to wind up with a weird mix of products. It is important that it's a 1 and a 2 step because LAH will react rather violently with water. Again, this is just a review, so I'm not going to hover on that one. What I do want to add to that is you have the option for a partial reduction. And no, it's not by controlling the amount of LAH, it's by modifying the LAH. So you'll see that the reagent looks similar. It's lithium and aluminum, but instead of 4 hydrides, there are 3 esters and 1 hydride. It's sort of like with a poisoned catalyst, we're modifying our reagent so that it's not as powerful, right? And we're still going to work it up with water. And this is what is going to allow us to stop at an aldehyde. Now, if you were working on this synthetically, you could always take this down to the alcohol and then use PCC. But if you want to do this in one step, and synthetically that can be really useful, you're going to use one of these more selective substituted lithium aluminum hydride reagents. Now, the R group can vary. In this picture you see right here, it's 3 T-butyl groups. What I encourage you to look for is that it's LAH, but with a little extra, right? You do not need to know the mechanism for this, but you do need to recognize this partial reduction. Another review reaction here, and that's the Grignard. I'm not going to keep doing the Grignard mechanism, but I will do it this one time in this chapter. You need an excess of your Grignard, but again, I would just assume that you have enough when you're working problems out. It's not always going to say excess or 2 equivalents, but you can't control the outcome by adjusting the amount of Grignard. You need enough. This is much like the ester that I know was introduced to you in the in Organic 1, at least if you took it with me. You're going to wind up with an alcohol, of course, but you are going to add 2 of the Grignard reagents. So if we look at the mechanism, and we'll do this on the next slide. All right, the first part of the mechanism, and let's do just a very simple Grignard. If we're doing methyl Grignard, you're going to attack your carbonyl and make your tetrahedral intermediate. So we've added a methyl, we have an O-. Now, if we had an aldehyde or a ketone, it would get stuck here, and then you would protonate in the second step. However, we have a good leaving group. So this is going to fold in and kick out chlorine. And we're going to wind up with a ketone. Now we know ketones are also reactive with Grignards, and there's no way to stop it. It's going to react again. From here, you have your second tetrahedral intermediate, and you've added 2 R groups. Now there is no good leaving group. This cannot fold back in on itself. So it's just going to hang out here until you add in something with a proton, acid or water. And there you go. You have your Grignard alcohol. You've added 2 R groups. Grignard is going to be important for pretty much all of these carboxylic acid derivatives. You are definitely going to be asked to give a Grignard mechanism at some point. You should review it. Something that is interesting that works with an organometallic, right? Grignard is an organometallic reagent. Gilman is another organometallic reagent. The Gilman reagent has 2 R groups, but only one of them is going to get added. It's got copper and it's got lithium, right? That's what makes it an organometallic. Organo and metals. You do not need to know the mechanism of this reaction, but this is one way that you can take a acid halide to a ketone. Right? We haven't seen a way to stop at a ketone yet. And so you can take whatever R group it is that you're looking for, Culi, and that is going to replace the Cl, right, the chlorine, with that R group from the organolithium. So we saw with our, let's go this way. We saw with our reduction, we could stop at an aldehyde with a modified lithium aluminum reagent. We can stop at a ketone with a Gilman reagent. All right, so there's a lot of reagents that you have to keep together in this chapter. To just emphasize that point, here is your summary slide. You need to know all of these reagents. You need to know hydrolysis, alcoholysis, aminolysis mechanisms, and Grignard. You need to know how to make the acid chloride, and you need to know how to predict all of the products. Klein does great work with these summary slides. That was just reactions of acid chlorides. I want you to keep that in mind. We're going to move on to acid anhydrides. And you're going to see in just a moment why this section's really short, but it's just as many reactions. When we talk about anhydrides, right, we're going to want to really pinpoint this leaving group. This seems to be where folks struggle the most. Just because it's larger, people have a hard time wanting to lose it. But this will leave just the same way as a chlorine. Now, what you're seeing on the first slide is an industrial synthesis. We're not often interested in heating to 800 degrees. That might be something our engineers might be looking at more in sort of a plant or factory setting. We're going to move forward and go to kind of our more standard synthetic steps. All right, or practical synthesis. Okay, so if we are going to prep, right, we started with prep. We always start with prep. So let's start with preparation here. You can make an anhydride from an acid halide, right? Those acid halides are the most reactive, so you can pretty much replace that chlorine with just about anything. For that, you just have to get your, what do they call this? Carboxylate ion. And you can make that by taking any carboxylic acid and just treating it with a little bit of base and pulling off that proton. This is your nucleophile. Your nucleophile will replace that Z, right? That leaving group. I'm not going to ask you for this mechanism, but it's a very straightforward mechanism, right? Attack, tetrahedral intermediate, loss of leaving group. Very, very straightforward. This is your most practical preparation for an acid halide. Notice they are comparing the leaving groups here as well. The reason for that is because every reaction we already talked about also applies for an anhydride. I am not going to go through each and every reaction again, right? The only one being different is the prep, right? How to make the anhydride from a carboxylic acid, or you can make it from an acid halide. Oh, I'm sorry. It's a carboxylic acid and an acid halide. So I misspoke. But you have hydrolysis, alcoholysis, aminolysis, reduction, partial reduction, Grignard, and Gilman. You would be expected to know all of these. I'm not going to go through all of them again. I will do one because I just want to show you how this will look as a leaving group. So what should we do? Let's do a simple aminolysis, and this might say 2 equivalents, right? Because that amine is going to be there again to pick up any acid that forms. Okay. You are going to attack your carbonyl. You are going to open up that pi bond. I will only give you symmetric anhydrides because there's no real reason to pick one versus the other here. So if you want to get a uniform product, you're going to pick a symmetric anhydride. We're going to get our tetrahedral intermediate. We've added NH3. That's a plus charge. O. There we go. This is going to fold back in on itself because we have a good leaving group, right? This leaving group is resonance stabilized, so it pieces out. We are now left with a protonated amide. You have 2 equivalents of that amine, or ammonia in this case, for this purpose, to deprotonate. And you make your amide. This is the exact same mechanism we saw with the acid halide, and that's going to be true for the hydrolysis, alcoholysis, and aminolysis, and the Grignards. You are still responsible for all of those mechanisms. You are also responsible for predicting the products of the reductions and the Gilman.